Hello. My name is Dr. Gary Holness, and today I have the privilege of talking to you a little bit about Internet of Things. Welcome to my workshop where I do a lot of electronics, tinkering, do things with robots, all sorts of electronics and programming, lots of fun stuff. So why don't we begin? And so a lot of you have heard maybe perhaps about IoT, and you've wondered what exactly is this Internet of Things? Well, as the name might obviously note, there's the internet, so there's connectivity, and there are a bunch of things, all sorts of devices. And this technology is, as we speak, revolutionizing many aspects of our lives. And so IoT came about from the confluence, the perfect storm, if you will, of lots of different things. The first one, I'll point your attention to the upper right-hand corner. It deals with the miniaturization and proliferation of embedded systems, microelectronics. And so you see computer chips in just about everything these days. In addition, the upper left-hand corner, networking, connectivity. Wi-Fi and other wireless modalities like Bluetooth are very commonplace these days. And because of the small form factor for the electronics, you can add network connectivity to virtually everything. So then we have in this lower right-hand corner, distributed systems, the ability to craft algorithms that work together among different processes running across computers scattered across the internet that give you the illusion of a single system. And so in this particular case, that's a depiction of a distributed multiplayer game. And then we have here on the lower left, software engineering, how you write code, a lot of productivity tools, a lot of libraries, a lot of software frameworks that make it easier to connect together applications crafted from all of these disparate devices. And so IoT is the confluence of many things, the three major ones: low-cost embedded processors, miniaturization, and electronics, and this easy network connectivity. This is what pushed these networking of these things to things as small as appliances, to things as large as automobiles, aircraft, and lots of things in between. And so what is IoT? You have a bunch of objects, physical objects, and these objects are embedded with sensors, the ability to measure things from the environment, actuators, the ability to do something, turn on a fan, move something, as well as computation. Now, that's particularly important because with computation in these objects, now you can make decisions based on what it's measuring, and those decisions will result in it doing something as appropriate. And as well as this distributed systems provides you the technology that allows you to connect and exchange data with all sorts of devices and systems in the internet. Now, the name of the game is not just to do it because it's cool, yeah, it is kind of fun, but also for some application. So let's take a look at one such application, smart meters in an electrical or power grid. Now, often during peak times of consumption, like in the summer when everyone has their air conditioning on, you're going to get a lot more demand for usage of lots and lots of electricity. Now, of course, there's only so much electricity to go around, and this happens especially in large urban areas. You have more demand for electricity than you have that electricity. So what happens? Well, if you can't service all this demand, it breaks the system and you get what are called brownouts. Now, with brownouts, what ends up happening is that there are whole sections of a geography that just doesn't have power. Now, that might be uncomfortable for some, like in the summer when it's hot and humid, but for others, it might be a life safety issue. You might have people at home that are on oxygen or other devices that are critical to their health and well-being. And so with a smart meter, you have devices embedded in your electrical power grid. And in the upper left here, we have a smart meter. And the smart meter has, of course, embedded systems and some computation and networking, and it communicates back to the power distribution center, the power company, about the consumption. And this is for every single house in some location. Now, with that, if you see that consumption is increasing and it's on a trajectory to outstrip what's available, that capacity, now you can send signals out to these meters to ratchet down the amount of power. So everyone gets a little bit less power, thus preventing these brownouts. Another application is a parking garage. When you have a parking garage, you have a number of floors and you don't really know if there are available spaces. In this application, you have sensor devices that are placed on each floor and they look at every single parking space to detect whether there's a car in that space or not. And so those spaces that are empty, that signal is collected and visualized here. You see this board and it tells you how many spaces are available on each floor. So then you don't waste your time driving around looking for a space. But these are, you could say first world problems, not very serious. But IoT has been quite revolutionary, changing the very nature of big things in our existence. And so to give you a little bit of the background, the United Nations predicts that by the year 2050, we'll have a significantly larger population, and even more so by the year 2100. And so, with all these people, of course, people have to eat. And this is going to put a lot more demand on our food systems. The food systems need to be able to serve all of those increased numbers of people who are demanding this food. And so, certainly, technology to the rescue has done all sorts of things, such as grafting and trying to grow hybrid versions of plants to produce more robust plants for yield and quality. You also have mechanization, all sorts of farm equipment, so one person can be more efficient in how and how much they harvest. You also have some biotechnology happening where you experiment with changing the genome and manipulating how seeds work for things like creation of plants that are more efficient in the water uptake. They're less quote unquote thirsty plants. And then we also have all sorts of sensors that measure things like nitrogen content, nutrients in the soil, moisture, and so forth. So you can take very precise inventory of things that affect or impact the quality and the yield. And so all sorts of things are important in in farming. There are weather challenges, insect pests, all sorts of things that impact plant health, both the nutrients, the temperature, the water, and disease, fungi, and bacteria, as well as the soil quality. How much does the soil absorb the water? How much nutrients does it have in it? Because that impacts ultimately the quality and yield of your agricultural products. And so IoT is used in this fashion. You have a lot of instrumentation that measure all sorts of things like wind speed, temperature, barometric pressure, and there are other sensors like we see here on the right that measure aspects of like soil temperature, nutrient balance, and things like that in the soil. And so you take these measurements, and the beauty of putting these sensors in regular increments across a field, it means now with specificity, you have increased a measurement on a real-time basis of the condition of your agricultural products, your plants, your crops in the field. And so the wonderful part about that is rather than waiting till the damage happens, you might see every 5 seconds, every 10 minutes, every 5 minutes, a new report with data about all of these factors that impact your quality and your yield. And so here we have our crops growing in the field. They're instrumented with sensors, and all of this data comes streaming in to a platform, a server system that accepts all of this data. And then this data is processed using all sorts of analytical tools, machine learning, and other techniques in AI. And then ultimately, you use that to make a decision. And for that decision, you apply an intervention. And this intervention might be the application of nutrients, it might be irrigation, it might be all sorts of things. And so here we see IoT, this network of all of these devices that communicate, made possible by electronics that are miniaturized with access to networking, impacting and revolutionizing agriculture in order to increase quality and yield to meet increasing demand that's placed on food systems. And so, yes, IoT is not just for parking, it also pivots entire industries that impact ultimately everybody. And so previously, what would happen on a schedule, for example, this is a crop duster in the picture on top, you would apply a blanket all sorts of chemicals and pesticides or nutrients onto the field on a schedule. And, especially for things like pesticides, long-term consumption of food items that have been subjected or exposed to pesticides can be deleterious to human health, and that's been documented. Moreover, by blanket application of nutrients, you get often, precipitation events like rain, and that rain tends to wash these nutrients from the field, effectively things like nitrogen runoff that poisons your water supplies. And so with precision agriculture, more so with specificity, where in particular on your field, there's a need for increased nutrients of certain types, and then or pesticides, and you might go off, and here we have an individual applying pesticides locally. And as you can see, the person is masked up. It's dangerous to be exposed to pesticides like this. It's bad for your health, but you're applying it locally. And instead of doing it locally manually, why not use something like a drone? Now, of course, the benefit of IoT is that more locally where you're going to apply instead of blanketing your entire field, leading ultimately to reduction in this blanket application of nutrients and or pesticides. And so here I have a picture of an agricultural drone, and this is with a farmer, just to give you a sense of how big these things are, the scale. And then we have a drone here that's in action flying, applying pesticides, and they can also apply nutrients to locales in a field. Now, the beautiful part about this is once you identify where locally you're going to apply them, there's all sorts of mission planning software where you can give flight paths. And we see here in this diagram a flight path. And then we have locations where these bubbles are, these push pins, if you will, and those are the drop zones where this thing applies pesticides. So you have local measurements, you identify specific locales on your operation where you're going to apply these nutrients or these pesticides, and then you deploy a drone for precision application, resulting ultimately in the reduction of this application of pesticides as well as nutrients, leading less to deleterious effects on human health, as well as less impact on water supplies due to nitrogen runoff. And so what exactly is this IoT system? An IoT system is almost like a robot. And to give you a little background about robotics, here we have a robot, Johnny Five, my favorite robot. And this is a so-called embodied agent. It has a body, it does stuff, and it moves in the environment. It is embedded or situated in the environment. Now, here we have our environment, and this robot has sensors. And the whole purpose of a sensor is to take a measurement of the environment. Now, this measurement happens again and again and again continuously because the environment is constantly changing. And so the reason for the sensing is to try to get a sense of what is going on right now, right now, right now in the environment. And so all of these measurements are taken in, and the robot maintains some computation. And what it's doing with that computation is populating some sort of data structure with a representation of what the prevailing context is in the environment. And so based on what this data structure, the information that it contains, and it's updated continuously over time, it runs some computation over it that's either trying to minimize or maximize something, achieve some objective. And then based on what that best or most suitable outcome is, it does something. And that doing something is accomplished by the actuators. An actuator, more formally, is defined as some device that projects energy into the environment. And that can be done in a number of ways. It could be mechanical force. So a wheel. A motor spins a wheel, that wheel exerts mechanical force, and it causes the robot to move. A motor turns a propeller, a rotor, and it causes the drone to move up, down, forward, or backwards. And so it can also be things like projecting energy, like a laser to obliterate a weed, for example, and there are robotic applications as well that do that. And so what ends up happening is this cycle continues. You take a measurement, sense, and then you populate your data structure, you optimize on some objective, and then based on that suitable outcome from this objective, it then plays some action into the environment, updating either the state of the robot in the environment or the environment itself. And so this sense, think, act cycle happens again and again and again. Measure the environment, perform a computation, do something. Measure the environment, perform a computation, do something. And so that's what a robot is. And when we think of IoT, we effectively take this robot and we break it apart and we associate each one of those pieces with a little bit of computation, some embedded system, as well as access to a network, be that wireless or some other, and it's usually wireless. Now, each one of these components then, these factored pieces of a robot, they can now interact with one another, and we use a network to do that, exchanging messages. So essentially, with IoT, each one of these devices that we connect to the network, you can think of it as a sensor, an actuator, or a small piece of computation. They interact with one another in a large system to perform some activity in an application. And so an IoT system is essentially a factor robot. It still implements the sense, think, act cycle, but all of the pieces are recruited across the network through some process or program that aggregates them, interacts with them, exchanges data with them in some type of application. And precision agriculture is just a big game-changing so-called killer app. And so in the IoT class here at Clark, it's actually one of my favorite classes to teach, we use an embedded system called the Arduino. The Arduino is about the size of a credit card, and it's an interface that allows you to arbitrarily read data from sensors or send commands to actuators to do something. And this is what the Arduino Uno revision 3 looks like. And this Arduino Uno is very capable and it's very inexpensive, about $30, $35 for the basic circuit board. And it can do all sorts of things. I'll direct your attention down below where it says analog pins and digital pins. It allows you to both read sensors and write to actuators to get them to do something. And so it runs computation, but where it really shines is in its ability to connect to things that interface to the outside world, namely your sensors and your actuators. Now, this Arduino can come in a number of different sizes or form factors. This, in particular, is the Arduino Nano. It's about the size of maybe 2/3 of a gum stick, so it's very, very small. And you can program this. It's maybe more limited in memory than the full-blown Arduino, but it is nonetheless an honest-to-goodness programmable embedded system. And something this size you could absolutely embed into a very small form factor. So imagine if you had a vest or a piece of clothing with lots of LEDs, light emitting diodes sewn in. You have this as your control board, fits in the pocket, you can sew it in. You could now have a dynamic display as clothing that you wear around. Very doable in current times. And so the Arduino Uno comes in many different forms. This particular one I use in my IoT class here at Clark, and this is the Arduino Uno Wi-Fi. Now, it's called the Arduino Uno Wi-Fi because it specializes in communicating wirelessly. And so one of the ways it communicates is with wireless internet or Wi-Fi, and it allows you very easily with the input and output pins along the top edge and along the bottom edge to interface sensors and actuators in this sense, think, act cycle over distances by exchanging messages. And so this also can talk as a Bluetooth device over Bluetooth wireless communication, and it can also talk wireless RFID. And so this Uno Wi-Fi is really an Uno wireless communication, and it communicates over various sensor modalities. And so you can connect, it also does cryptography, so you can protect your communication, and it also has inertial measurement units. So when you move this thing up, down, rotate it, or what have you, it has sensors built in to do that. So you could effectively haptic applications. Let's imagine as a kind of joystick, like an air mouse, for example, if you move it up, you could literally write an application that reads that movement and then responds with a cursor on a screen, for example. And so this is a very versatile tool. It implements also TCP/IP protocol stack, transmission control protocol, internet protocol, which is the standard for internet communication. So this device can natively talk to websites, talk to anything that you can access across the internet, including your computer. And so here, this Uno, it has signal pins that allow you both to read sensors to measure what's happening with the outside world, as well as send commands to actuators. And these things are programmable. So they're two-way. You can set them up to read inputs, or you can set them up to read outputs. And programmatically, you can change this up, which is kind of nice. And so here, you can use this Arduino. There's a whole ecosystem of expanding its capabilities through so-called daughter boards or shields. And these are other boards that have pins that mate with these connectors, and they extend the capability in all sorts of interesting ways. And so if you can imagine an application, I guarantee you there's a shield for that. This shield in particular is the so-called Arduino motor shield. And so you plug it into the input-output pins. You can see here in the upper left being plugged in. And down below, that's what it looks like when it's been plugged in. And so this allows you arbitrarily to control motors. Those could be servo motors. Those could be regular torque motors. You name it. It can control your motors. And the nice thing is that you send a command to this shield, the motor shield, and it has the logic encoded in it to appropriately send the right signals to control your motors. And so you don't even have to know the details of motor control. You get yourself a motor shield and just give it high-level commands like, here's the velocity for a torque motor that just spins, or here's the angle you should move for a servo motor. And so there's another interesting shield, and I can't possibly go through all the different shields there are. There are just hundreds of them, literally. This is called the eHealth Sensor Shield. And what this does is allows you to interact with various health sensors, things like a position sensor, a blood pulse oximeter, a blood pressure monitor, core temperature, things like respiration, and an ECG for reading someone's heart signal. And so I've actually, in my work, I've taken one of these, and these are some pictures from it, and created a system that you can use to build processing pipelines for clinical monitoring. And this is intended for home healthcare. And so with this, you put together these processes in an internet, an IoT network, a sense, think, act, and you wire it together with computations to report into a data center that then sends SMS alerts should, for example, your heart rate go too high. And so this is something probably you can build. I know the Arduino is about $35. The eHealth Sensor Shield at the time was $200, but you can build for $250, $235 rather, a very sophisticated monitoring system. So that was a piece of research I did at my previous institution. And so I did that by implementing the following stack. I had the Arduino Uno at the bottom. I have the health sensor shield that allows me to get sensor measurements from various clinical sensors. And then this Zigbee shield allows you to send wireless signals. And then this Wi-Fi module converted that to internet connectivity. And so I implement for this a web server, and that web server, you connect to it over the internet and pull web pages that are self-populated with values for each one of these health sensors. And so all sorts of shields, and there are many more than this. There's the motor shield I had mentioned, health sensor shield I showed you an example of. There's a GSM cellular shield where you can actually make phone calls over the cell phone network. There's a CAN bus for controlling all sorts of industrial devices. There's a data logging shield for logging data for various systems. So let's say, you have a trail cam that's watching wildlife go through an area and you want to log down those videos. A data logger is something you can build yourself. There's the gyro accelerometer. So you can look at motion, angular velocities over time. There's a radar shield. all sorts of things, you name it, literally hundreds and hundreds of shields that extend the basic Arduino capability to all sorts of applications. So the sky is truly the limit. And so the development tools, when you program an Arduino, it comes with a rich suite of tools that you can use in order to write programs on this. And one of the things you need to focus on was how you program this device. And so the Arduino IDE, or Integrated Development Environment, it's available for free. All of this is open source and free, gives you a cross-platform graphical and visual way for writing programs. And so when you install it, okay, the first thing you do, you download it, you write it onto your computer, you install it, and then you plug in your Arduino device, you verify your system can actually detect the device, you write your program, and then once you write your program, you issue a command through a click to load it onto your device, and you're off and running. And so one of the things you can install is the base library for controlling the digital input and output and analog input and output and running programs. But there are also specialized libraries for communicating over Wi-Fi, for example. And so this is a snapshot, a screenshot of the Arduino IDE. And so in this, there's a field where you can write your program, and it does syntax checking to make sure that you're writing appropriate commands in your Arduino IDE. And down below is a little data window that shows you what your progress is. Once you compile this program, and when you're ready to upload it, this data window tells you about what the process is and how it's going. And so the programming language for Arduino IDE is a subset of the C++ language that they call Sketch. And this program is a so-called strongly typed language. With this, when you define variables and data types, you have to tell it precisely what type of data is stored in these variables and these data structures. Take, for example, in this example, we have an integer called num iterations, and it's initialized to 10. Here we have an array of characters, 10 positions long, and they're all characters. And then is present is a Boolean type, and it's initialized to false. It's also so-called block structure. When you think of a program is a sequence of commands that are executed and they have meaning, and a collection of commands is called a block. And so here, this particular block called my function, you can call it and use it as any kind of function. So you give it a name, and then you give it the beginning of the block, which is the open curly brace you see here, and the end of the block, which is the closing curly brace. Now, if I were to take my pen, it's called a block because I can draw a rectangle around this unit of behavior, also called a block. Now, this is a function, but inside of it, I have this while loop. And what a while loop does is it executes something again and again and again and again and again until some condition either passes or fails. So I have this while block, and it has the opening curly brace here, and the closing curly brace. I can draw a rectangle around this while loop, also called iteration. And so the purpose of this function is to get the condition of a bump sensor. That's another function. And then it iterates again and again and again, detecting how many times that condition held true. And so when you have a particular command in C++ or in this subset called Sketch, you end that with a semicolon. And so this first command ends here. Is bump is going to get the result of calling get sensor, and that command ends. Backup, that takes a parameter, how many, and that command ends here. And so it's block structured, explicit or strongly typed language, and you have to terminate each command with a semicolon. Now, Sketch is so-called compiled language. And with a compiled language, you start out with your program, and that program is a high-level specification that's meaningful to us. In Arduino Sketch, a program is a file is called a .ino file. That's just what they've chosen to call it. And then you run it through the compiler. It translates that into machine code, which is just a sequence of ones and zeros that's equivalent to each one of these commands in your program. The whole reason for a program is because It's a lot easier for us human beings to understand. Instead of saying 10111, we'll say hello, right? It's a lot easier. And so this translation is called compilation. And then after you get these ones and zeros, your machine code, which is understood by the processor, by the electronics, you then stage it. You load it from your IDE, your development environment, onto the hardware. And so in this compilation, it checks the correctness of your program to make sure you've used these statements in the appropriate way before loading it onto the board. And so now you take this program that you've implemented, and then it goes through the compiler through that program more than one time. First, you have pre-processing part of compilation, and that preprocessor, it takes these synonyms, if you will, that make things easier to understand, and translates them to the program, and then it compiles them. And so all of this happens before you do the staging. The preprocessor translates things. So for example, imagine if you had something called num iterations. Now, imagine you're going to do something 10 times. It's a lot easier to understand num iterations, num iter, rather than just to have 10 everywhere in your program. And so the whole purpose of this preprocessor is so that you can define these synonyms or so-called macros that you substitute in your program, and it makes it a lot more readable. And so then once you translate your program to machine code, there's another step that happens. Your machine code is going to use different libraries of functions and utility routines already defined for your system, like send this across the wireless network. You need to get those machine code bits and bytes that are for the implementations of these libraries. And so your compiler then goes through a process called linking. And with the linker, it takes the ones and zeros for your system libraries and combines them with the ones and zero machine code for your compiled program, and that becomes your system image. And that system image is what is actually loaded onto the Arduino hardware as your program. And so your libraries include all sorts of very useful commands, things like how you read, and write from and to your devices that you attach to it, looking at the directionality of these pins or these interfaces on your hardware, whether it's going to be sending data outbound or reading data inbound. Similarly, for the analog, digital just deals with ones and zeros, binary, but analog deals with levels of voltage, analog or real valued quantities. Now, we also have ways of controlling devices that are so-called serial, how you send sequences of data in and off of the device. And so this is an example of the Wi-Fi library. And this Wi-Fi library makes it a lot easier to deal with wireless communication. Those functions, those blocks of behavior have already been implemented for you. And so you would include this Wi-Fi library with your program if your program was going to receive data over the internet or send back responses or data over the internet. And so here, there's a lot of complex behaviors that you could imagine when you implement this sense, think, act behavior. And in the IoT class taught here, Clark, we have finite state machines and a bunch of other methods for how you structure them. And so with that, a finite state machine starts with a graphical depiction of some algorithmic execution, a sequence of steps to accomplish some end. And with that, we have a state, and a state is depicted here as a circle, and this circle corresponds to some behavior or some set of commands or blocks of behavior. Now, there's some sort of input that happens, and that's typically an event or some piece of information from a sensor, and that event or sensor feedback or sensor measurement is depicted here as an annotation along each one of these arrows or edges. And what that represents is the triggering of the ending of one set of behaviors and the initiation of another set of behaviors depicted here as state number 2. So in this fragment, we have behavior state 1 occurs, And then the moment a certain measurement is detected, then we transition to this other behavior we're calling state two. And so with this, we can structure very complex sets of behaviors and interactions in a very methodical way using this finite state machine. And so one of the examples that we go through is a recipe or scheme for how you develop these finite state machines. You start by defining your states. You create a construct called a switch or conditional execution over the states. You establish all of the transitions between behaviors or states, and then you add the conditions based on what happens from sensors, and then you add in the functions from both the function library given to you as well as functions that you write. And so with this, the framing application is a robot. And this robot is going to engage, in this example, in something called bump and turn. And so what happens, the robot begins moving forward in this direction. It decides, bumps or detects a bump, like bump into a wall. It then turns 180 degrees, reversing its direction where it's pointed, and then it proceeds forward. And so with this, our algorithm is going to be to move forward some small distance we're calling d. And it doesn't matter what d is, it's just some distance. You check the bump sensor to see if it has bumped into something. If it hasn't bumped into anything, you go back to step one, continuing forward. If you have bumped into something, you turn around some angle, we're calling angle A. A just happens to be 180 degrees in this example. And then you step down here in step five, go back to step one. So you keep doing this again and again and again. How we depict this as a finite state machine, we start out going forward. So we're in this forward state or this forward behavior. We then, oops, changed my slide here. And then we transition after some amount of time, gone a distance d, to checking the bump sensor. So we check the bump sensor and we either get no bump. If it detects no bump, we transition to going forward again. If it detects bump, we go to transition to this turnaround state. And then after the turnaround state is done, we transition back to forward. Now, one of the things you'll notice here, this check bump state, it has two arrows leaving it. That means that there's going to be conditional. We need to evaluate if something happens and make a different choice based on whether it is true or it is false. And so in this example, we have our states here, and there are certain prerequisites you need for Arduino Sketch. You need a setup behavior. This is our setup function. Let me get my pen out. And this setup block is for initializing the pins and setting whether you're going to take inputs through them or send outputs out of them, as well as how you do this sequential communication. And so if you had Wi-Fi, you would join the network in your setup function, your setup behavior. And then this loop behavior is called repeatedly. It starts in the block, it runs whatever commands are listed, and once it exits the block, it goes back and then it calls it again and again and again. This is where your repeated behavior occurs. And so with this finite state machine, we start out with our states. We're going to define some values using preprocessor macros or synonyms. One is called forward. The next one is called check bump. And the next one is called turnaround. So you notice here, for each state, we have a different number, and this is going to be the state's identity. So we start out and we initialize a variable called state. It's going to be initially going forward. So here we have an iteration. Again and again and again, we're going to do something. And that do something is evaluate the state and engage in a different action based on what that state is. So here we have a switch, and a switch is a conditional execution. And here we have something we're going to do if we're going forward, something we're going to do if we check a bump, and something we're going to do if we turn around. And so what happens with this switch, we iterate through the while, and then each time we come into the state block, that is a block of behavior. Let me just identify the block. And then depending on the value of the state, if that value is forward or 1, we're going to execute what's here. If it's check bump or 2, we're going to execute what's here. If it is turnaround or 3, we're going to execute what is over there. So now we want to wire in the transitions. We have here what I call a switch sandwich. And for the Arduino, this iteration is accomplished by this loop. It's called again and again and again by the processor. And so here we have our continuing on. Each one of these cases, each conditional execution, we're going to fill in the guts of what happens. And so when we transition from forward to check bump. So what's the last thing we do when we're inside of this block for going forward? The last thing we're going to do is set whatever the new state is. If the transition is going to be into check bump, then we set state to check bump. And then when you drop out of the switch, the next time around, we're in this iteration, we're going to select that check bump. And so how you set programmatically these state transitions is by setting this variable here called state to whatever the next thing is. So that's going to be the next behavior. Okay. So now we're going to do the same thing with check bump. We're going to pick, for example, no bump. The state is going to be forward, and that represents this transition. And then for turnaround, we're going to wire in that transition to go to forward. So we say state equals forward. Again, that is the next thing to do after you are turning around. So after turnaround, your transition, your arrow goes to forward. So now we're going to focus on this check bump. And recall, we had two arrows that are going outbound from check bump. And so that means we want to have a conditional that says if something happens, we're going to pursue one transition. Otherwise, we're going to pursue the other transition. So that's where we're going to test things out. We're going to put in a bunch of prints so we can see that the states are actually happening in the order that we designed them to occur. And then you'll notice here in check bump, I have this conditional. This conditional is an if statement. It says if it is bumped, okay, and I have a variable called bumped, you're going to set the next state to turn around, which is here. Otherwise, else, there's another part of the conditional, it's going to go forward. So I set that. So now I've wired in all my transitions. And this is a methodical way of constructing these finite state machines, which are an implementation of very complex behaviors. It can be very, very complex, including between a communicating client and a server over a network. And so after that, we then go to our API and we enter in the commands that implement what these behaviors are. So going forward might be this drive command with the speed for each one of the wheels, the left wheel and the right wheel of the robot. Is bumped, we set it from an API called get bump sensor to actually physically read the sensor and return back the bump condition. And then turn around, we have a turn command, and that's from the API, the robot, and we give it the angle in degrees for which it should turn. And so here we have a methodical way of implementing this complex behavior by translating this graphical depiction into this code. And this is a prescriptive recipe that I teach to my students in IoT class. And so some examples of using that, something called the bounce chaser. And the bounce chaser uses a finite state machine and some light emitting diodes, LEDs, that oscillate in which one is turned on, and that turning on and off pattern moves to the left and moves to the right. So the first thing I do with my students, I give them the parts list and I give them a description of the task. And so here, the LED begins in one position, and they're all the same color. You could make them different colors, but that's not part of the requirements that they all be the same color. But the first LED on the left lights up, and then the next one, and then the next one, and then the next one. And then this pattern of lightedness, it changes order. It turns around, and it goes back, and then it goes the other direction, and then it goes back again, and it continues in that pattern. It's bouncing, and it's sort of chasing around to the left and chasing around to the right, hence the name, the bounce chaser. And so here, they use this recipe for writing a finite state machine, and they implement the bounce chaser. And this is first or second project in the IoT class. And so here in this lab investigation, you're required to keep a lab notebook because you're going to be doing a lot of experimentation and writing down a lot of things. And so I also, we go over how you log entries in a research notebook. How do you build circuits on a breadboard? Because students haven't used this thing called a breadboard before. And that breadboard, let me go back, is for prototyping circuits. And so with this breadboard, you have connections and conductors, and you're using wires and components to wire these things in. So you learn a little bit of electrical engineering about electronics in IoT class. And so we have this notebook, and you need to write down a bunch of things about how you send input, how you get input into the board, and how you send output to the outside world, how you read this thing called a resistor that you need in order to shape the voltage to either light or unlight the LEDs. And then it's not about studying, it's very much about experimentation. Roll up your sleeves to jump in, design it first. Design is very important. You don't just willy-nilly just start plugging things in haphazardly. You have to design before you implement. Excuse me. And so here, this is a circuit diagram. And this circuit diagram takes digital output from the Arduino board, and it sends that through a 220 ohm resistor, and that's needed to shape the voltage and current to the right amount to light up this LED. And then this is the diagram, circuit diagram for LED, and this symbol down below that represents ground. And so they learn all about the underlying electronic concepts needed in order to understand design and ultimately build these circuits. And so, excuse me, there's an example of a lab notebook, and part of their assignment is to make lab notebook entries, which they are required to submit, and they receive part of their project grades based on the lab notebook. And so let me skip past these APIs, and this is an example of the bounce chaser. Let me see if I can show you a little bit of that. I'm not sure if the sound will come through on the microphone, but at minimum, I've included all the URLs to these videos on YouTube so that you can look at it on your own time. So let me start the relevant part of the video.
So this is incrementally effectively bounce between this thing with 5 volts to keep them continuously. We're going to drive them from the digital I/O lines, which are here. You just pick 4 of them. Okay. So this gradually changed.
And so what I do is I give them the parts list, I give them the task, we have the technique for how you write the software, and then sort of like cooking shows, I show them what the finished product should look like. And so this is the finished product.
I/O lines, which are here. Just pick 4 of them. Okay. This is the finished product of sorts for the 4 LED bounce experiment. And as you can see, 4 LEDs are lit, traveling, going far enough.
Okay. And so that's the bounce chaser. We also have instruction on how you do input and how you do output. It's really important to understand how all of this works programmatically on the Arduino board. And so with this, you have to set up the bits for how fast you communicate. And then we can see here in this command, pin mode, you're saying which pin on the board to control and what direction is it set up for. It's either set up to send output or set up to receive input. And then in the loop that runs again and again and again and again, we're writing out something to this output pin, and then we delay some amount of time, and then we're writing something to this output pin. In this case, we're writing a high signal. High means 5 volts and low means 0 volts. So we're turning on and turning off. And that's exactly how the bounce chaser works. Now with inputs, it's a little bit different. You'll notice here the setup, we set up a certain pin to be input. So data is going to come in. And we use this digital read in the loop. So it runs again and again and again. If that value is high, we're going to do something. If it's low, we're going to do something else. And so we have the digital input and output, and we use that in this application. And so with the application, they also learn a little bit about some of the physics underlying some sensors, as well as how to program and how to use the sensors. And the two particular sensors they use in this next application is called the pyroelectric. It detects body heat around 98 degrees temperature Fahrenheit, which is body heat. And we interface this to the pins of the Arduino, and then they write an application to read the presence or detect the presence of a person. Now, this is the first time in this project at the juncture in this semester when we have this project where they're doing actuation. They're sending output to the digital output port, and this particular output they're sending is a so-called square wave. So they're turning off the voltage for a time, they're turning it on for a period of time, turning it off and turning it on at a particular frequency. And this frequency, this output is used to drive a buzzer. And based on the frequency, you can actually play a song. And so coupled with the body heat detector and the buzzer, they play a song when it detects a person has come by. And I call that the AHA alarm. And the song it plays is a song by AHA, which is a band from a long time ago. And so I'm not sure you can hear this. Let me just try to play a little bit of it.
So have signal. So the signal wires for the 8 for that is it'll play take away when it senses the presence of a person. So let me move my hand away.
And this project was a little bit annoying to some of my colleagues because I had my students all throughout the building playing this song and setting it up in windows and classrooms and stuff like that. But nonetheless, this is another project. In this project, they're building a device that responds to the detection of people in the environment and does something, plays a song on a speaker, on a buzzer. And this next one, we pivot to a lot more complex input and output, specifically for driving and controlling a digital display. And so this is the wiring. As you can see, there's a lot of signal wires that do lots of things. And when you send output to a digital display, you have to give it a location and you have to give it an encoding for a character. So there's a lot of complex things going on, which you can easily structure in a finite state machine. And so this is some of the wiring diagram, and you have all the pins in a sequence, and then you cycle through them and push the right information through the right pins at the right time through your digital write command. And so this is another sensor. And the goal of this project was to do some environmental sensing. This particular sensor senses humidity and temperature. And so they're reading input from this device, and they're sending output of certain types of text out to the digital display. And so this is what the wiring looks like. It's a very simple circuit, but the hard part, or the more challenging part, complex part, is the digital display. And so there's, let me just show you, there's two parts to it. We have
Diagram here we have.
This was the control of the display. Let me just go forward to the actual environmental display.
Hello, this is the final version involving our sensors and our actuator. Here, of course, we have the Arduino Uno Wi-Fi revision 2. The Uno feeds using DuPont wires.
And as you can see, it displays the temperature and the humidity and cycles through a bunch of messages on the digital display. And so again, this is the finished product. They receive a parts list, a reminder about the API calls, and then we have a design session as well as a demo of what the finished product should look like. And so we then pivot once they have instruction on how to program complex behaviors, familiar with the APIs, about how to read from sensors to send out to actuators. Now we pivot to networking, and that's where they learn how to get data off the board, as well as data onto the board. And so with a network, they need some elements from computer networking. And in computer networking, we talk about different devices that are attached at the so-called edge of the network. These are your clients and your servers. And then we talk about the interior of the network, those devices that store and forward chunks of information, ultimately making its way from the source to some destination. And so in order to understand how to do networking, you have to understand what the different components are collectively that comprise a computer network. And so we also talk about encapsulation. And this diagram, this dynamic or this animation talks about when you send data, there are different sets of processes that do something slightly different with this data ultimately to make its way across the network. And so at the endpoints, at the source of your message and the destination, it implements 5 different types of behaviors: the application, transport, network, link, and physical. Application deals with what you see in your program. Transport deals with maintaining a single location and getting that data to another single location. The network deals with these intermediate steps among all these pieces of hardware called routers and switches that store and forward your data chunks, ultimately making its way to the destination from the source. And then we have the link layer, which is responsible for encoding the logical data into physical data. And so physical data, when it travels across the network, it's either electricity at a certain frequency, or if you're dealing with fiber optic communication, it's pulses of light, laser light at a certain frequency. So the link layer is responsible for that translation both to the physical representation as well as physical representation back to these ones and zeros. And so here we have a description, and we cover this in IoT, about how you lay out your programs that are scattered across the network in this distributed system. There are 2 major roles. One is called a client and one is called a server. Every program that runs on your system is called a process. And a process is just runs. A server process is that principle in an end-to-end communication that receives some message, interprets the message, does some work, and then returns back the response. The client, on the other hand, is that process in your communicating endpoints that initiates a request. So when you take your browser and you say www.clarku.edu and you hit enter, your browser is a client and the server is a web server somewhere in a data center that's giving you these requested web pages, which you then get back and your browser draws it on the screen. And so a so-called client-server architecture is one model for how you create software where the 2 pieces of this software interact with one another across a network. And so when you deal with pieces across a network, particularly in this sense, think, act, exchange across components in the internet, you have to think about how you get this data. And so in this diagram, it's an example of something we call data pull. And data pull says you have the client, it requests something, and it sends that request across the network to some, say, sensor device. The sensor device, like get the temperature, get the humidity, or is there a person detected here? It performs some work, gets that measurement, and then returns back a response to the client that requested it. Now, with this data pull, the client requests that data, and it's thought of as pulling back that response. Now, this is a very simple thing to implement, but one of the drawbacks is if you request a lot of data again and again and again, for each piece of data, you have 2 messages round trip. You have the message that's going from the client forward to the server and the server's response back to the client, and that can overwhelm the network if you're dealing with a lot of message data. And so again, if this client wanted a second temperature measurement, it would have to request again explicitly. Okay. And so there's another type of data exchange, and this data exchange is called data push. And with this data push, what happens when the client requests something from the sensor, it doesn't request a single measurement, it stores a registration or sends a registration that says, I'm interested, for example, in the temperature measurement, and I want this temperature measurement every time you have it for the next 10 minutes. And so once the server gets that, it stores that registration and says, aha, well, this particular process running on the network is interested in temperature measurements, and it tells me how I can contact it, and it tells me how long it wants it. So anytime a temperature measurement is available in this sensor device, or the Arduino to which the sensor device is connected, it's going to send a copy of that measurement to everybody who has a registration stored. And so when the client registers, the sensor or server stores the registration and then sends back a request that response to the client that says, yes, I received your registration and you're ready to go. So then the next time, in each case, in time over that, say, 10-minute period, every time a temperature is available, it sends that temperature to that particular client that was registered. So it sends a temperature again. Temperature's available, sends it again. Temperature's available, sends it again, and so forth over that period of time. In this case, from our example, is 10 minutes. Okay. And so that's our data push. And we use that in a major project in IoT for environmental monitoring. Now, with that, of course, we have our measurement, our start time, how often that measurement should be sent in our registration, and the duration of time over which it should send it. So this is exactly a lease, like you rent an apartment, right? You rent an apartment for 12 months. It starts at a certain time, and then each month you're going to make another payment for your monthly rent. It's the similar concept. So with this registration, we introduce another device called the Raspberry Pi, and it runs Python programs written in the Python programming language. It can run them. It runs them very easily. And then we have that Python program talking to the sensor devices, which is an Arduino Uno Wi-Fi with various environmental sensors and other sensors that are interfaced to it. And so in this, our Python process or program, it acts as a registration client that talks to the registration server of the sensor device. And so the client initiates the request. Could you honor this registration? And then this registration server interface or role returns back to the client, yes, I got your registration and I'm going to honor it. So now the sensor device, when it sees this temperature measurement at this time, for example, it acts as if it's a data or temperature delivery client. And it initiates a request that says, hey, I have a temperature for you, temperature T. And then the server does some work of storing that, and then returns back a response that says, yep, I got your temperature. And so here we have two roles. We have the client role initiates the request, and we have the server role initiates a request. Now, any process that implements both the client and the server is called a peer. And essentially how this environmental monitoring system is implemented is as a so-called peer-to-peer network. We have a Python client talking to an Arduino Sketch device. Now, one of the beauties of communicating over a network is that you can have different hardware running different software being able to interoperate or talk with one another, which is why networking is so powerful. So now we have in our system, if you can have one sensor, you can have many sensor devices. And so in that case, our Python program, it registers with the first sensor, got the registration. It registers and gets registration in with the second sensor. And it does that for some number of sensors, in this case, the third sensor. So then after some point in time, sensor measurements come in from the first sensor, from the second sensor, and the third sensor. And all of this happens over time on some schedule. So there's a lot of data streaming into this Python server. And so this Python process, rather, it has a file system that it uses to store all of this data that comes streaming in. And so in order to make that all work and to scale, it implements an operating system construct called threading in order to be able to accept all of this concurrent measurements of various sensors from the environment coming in across the network. And so now, in this case, we have our sensor device and we have an Arduino Uno, and we have things for the presence of people, temperature, and humidity. We have other things for radiation, for sense, for fire, all sorts of things. And so this runs and sends data by registration to a Raspberry Pi running Python. This is an example of the Raspberry Pi board. It's a small board computer running the Linux operating system. And as a small board computer, it can run Python, C, C++, what have you. But we use Python on this board as this node that registers to receive temperature measurements from more than one Arduino, off of which is interfaced all of these different environmental sensors. So now, once it gets all of this data, it plots a time series. They can visualize that both in terms of the time series, which we see above here, about how these measurements proceed over time, a different color line for a different sensor measurement. And then we can also compute a histogram and do all sorts of amazing things, such as use the SMS gateway to send an alert to say, hey, there's a person in MACD 002. Hey, the humidity in MACD 002 is now over 52%, for example. And so when you see this, you might think, gosh, well, this seems quite familiar. Where have I seen this before? This looks a lot like the IoT killer app for smart farming. Only the sensor modalities might be different. Yeah, some of them are the same, like temperature and humidity, but you might have sensors that are inserted into the ground for things like soil quality, moisture, nutrient content, and other essential nutrients. And so here we come back full circle. And in the IoT class we teach here at Clark, their students are given all of the tools and technologies and background needed to build a serious system to impact all sorts of domains. And so that's all I had to say. I hope this was helpful to you. If you have any questions, please do not hesitate to reach out to me. IoT is a lot of fun. You learn a lot of things while making a difference in all sorts of ways. So have a great evening.